Hi, my name is Lisa Richter. I'm the Director of Industry Outreach and Growth for CSIA. Welcome to the Masterclass. Before we get started, a quick word about CSIA. Probably most of you here today are familiar with the association, but if you're not, all you really need to know is that CSIA's mission is to help SIs build better businesses. How do we do that? Well, for starters, we have a team of volunteer SIs who have crowdsourced a best practices manual to help SIs scale their businesses. In fact, the BP manual regularly reviews and updates the manual, currently on its sixth edition, and the committee is already planning for the next version. For those companies that want to take the best practices to the next level, CSA also offers a certification program that includes a third-party audit. Many companies find that this audit is extremely helpful for them to deeply understand their business and how they can scale. With thousands of qualified integrators and suppliers, the CSIA Industrial Automation Exchange helps SIs, industry suppliers, and manufacturers connect and do business. For SIs and partners, it provides a platform to support your content and SEO marketing efforts, position yourself as a thought leader, and nurture prospects during their complicated buyer's journey. If you are not currently a member, now is a great time to join. Membership provides you and your entire team a full lineup of virtual events and other resources from accounting to sales to operations to training 365 days per year. If you just want to get a flavor of CSIA and its members, I encourage you to listen to the Talking Industrial Automation podcast. CSIA members talk all things industrial automation, and it's just a great way to hear what your peers are up to. Couple of housekeeping notes before I turn it over to today's speaker. If you have any questions during the presentation, please use the Q&A feature in Zoom. That helps us stay organized. I also ask that you please turn off any automatic note-taking applications. Those are against the CSA's policy at this time. Thank you for understanding. That being said, the session is being recorded and you will get a link to the recording in the next day or so. At this time, I'm going to turn it over to today's speaker. Mike, take it away.
All right, thanks, Andrea. Get my screen shared. Okay, today's webinar is going to be on maximizing SCADA project engineering lifecycle. I'm Mike Brost. I'm a lead solution architect with AVEVA. So we're going to focus on, just the system integrator role in a project workflow, building, standardizing, commissioning, uh, getting a system up and running, bidding for it, just the whole project life cycle. And so, we all went into control system engineering, and I'm a terrible typist. My goal was not to be a typist. My goal was to solve problems, improve operations, increase safety, higher efficiency, better sustainability, all these great things. And we end up having to do, a lot of typing to get our job done. And so let's try and get away from that and look at techniques and how we can minimize the amount of, I'll call it brute strength and awkwardness that we have to pursue in order to get something going, right? So, stop designing with the techniques of chaos and brute force, right? Individual tag configuration is an error-prone process that introduce all kinds of one-off things. Rules and models bring intelligence to the SCADA design process, right? We can't be relying on security from graphics anymore. We got to look at a different approach to how we secure the systems. Information should be a fundamental part of the SCADA design, right? Many things need to leverage that informational model that SCADA provides and use it higher up in the food chain. We want to be able to create a UI once and view it from multiple device technologies. We don't have to be rebuilding everything every time we want to add a null monitor or go from a one monitor system to a two monitor system or go to a tablet or a phone or any of these things, right? And our device connectivity is probably the most unique and inconsistent part of any SCADA system. And so we got to make this thing more adaptive and more model aware so that we don't have to completely re-engineer things as we change from one brand of device to another. Right. And we like to keep our physical deployment of the SCADA system should be independent of the SCADA application design as we go from a test bench to a commissioning bench to a full production implementation. We don't have to rebuild the application as we go from one place to another. If you have to rebuild it after you've tested it, it's no longer tested. So you have to test it again. So as we move into a SCADA design, let's get away from a tag-centric model to an asset-centric model, right? And look at the SCADA system from the asset perspective, right? Assets, tags are just one aspect of an asset. Historical data, security, alarms, architecture, connectivity, documents for the assets, designing all these things, make it all possible to build a SCADA system. If we looked at a classic SCADA system and it only handled one asset, it would be just like this. It would just be here. This SCADA system runs a power meter or runs a variable frequency drive or runs a lift station or a aeration basin, and everything about it would be all included in that one thing. But yet that's impractical. We have to throw a bunch of other things in there, and we want to end up with something that is organized and is adaptable and becomes easy to replicate, eliminates errors, and eliminates, more importantly, all the effort required to do this. So to do this, today we have great enabling technologies, right? We have generative AI, but in order to make AI work, you got to have structures of data. You got to be able to make AI aware of those structures. You got to have models that you can have AI generate for you. AI has to also be educated on how to build those models, and including graphical content, right? So it's schemas for that graphical content. We need to be able to put things together and tell AI, hey, build me a screen that does this, right? And we have a lot of examples of this up at AVEVA's GitHub, if you care to go there. But now we look at something from an asset type, right? And an asset type is, an example here would be, what if we wanted to build a SCADA system, looked at every airplane in the world as it's flying around, right? We could go to AI and get this data. AI can process it, can build me templates for all my airplanes, every model, every type, every vendor, every manufacturer, every airline. And let's just go. We actually did this. This is kind of a fun example, right? So let's build a system, right? Let's create airplanes. Let's find all the different brands of airplanes. Let's create these things. We just had AI build this for us. And now we have organize it by carrier, tell it to build me a screen, you know, so I can visualize every aspect of every airplane. It'll go through and say, yeah, I can do that for you. I can make a screen. I can put it all together. And there it puts out a faceplate that describes the airplane. You put it in a runtime. You can then create all your instances of your active airplanes that are running around currently flying, see where they're going, what their destinations are, everything. And this is all web-based information. And we just basically said, hey, build me a SCADA system to go monitor this. Put it on a phone, put it on a tablet, put it anywhere we want, and do it with very little effort. And more importantly, increased accuracy, right? We don't have to worry about, if one airplane works, they all work. And look at this more practically. Like, let's look at a power meter as an asset type, right? We'll pick a Schneider Electric Ion 6200 power meter, right? There's probably a little over 150 parameters in that power meter. Do I want to type every one into my SCADA system? Do I want to create tag for every parameter and then duplicate that parameter for all the 100 power meters that I may have? No, and then there's different variants of that power meter. You get the kilowatt variant, the megawatt variant, and there's different ways you want to talk to it. Maybe I'm going to talk to it directly with Modbus. Maybe I'm going to go through a PLC gateway and an array UDT to talk to it, right? And then I want to create visualization for that meter. Maybe just show the main parameters. Maybe you have a detailed meter information, which shows lots of data, right? And I could build a little wizard on my power meter asset and say, hey, what are you? What's your type? How are we going to talk to you, right? What communication style are we going to use? And then how is it going to be historized? Is the power meter going to be scaled? Is the signaling different? This can all this used to be have to be typed in manually by hand, or edited in a spreadsheet, or done something, which is a very error-prone process. And now we can simply say, use AI to build this for me and create me my power meter, and then read my P and ID and create my 100 power meters in my plant. So we look more detailed into what really we can do with an asset type. Is that an asset is a multifaceted source of information. It defines how we want to see the asset, what data we want to have the asset tell us, what part of that data is coming from devices, what part is coming from humans, what part is coming from other sources of information. What do we want to store in our historians? How do we want to organize it? How do we want to calculate metrics about it? Any sort of logic, scripting. How do we want to optimize the asset? What do we want to do for this, right? And really lower the total cost of ownership of how you do this, enable rapid rollout of changes, really get rid of the traditional effort where we spent lots of time doing repetitive tasks that really add very little value by themselves. I mean, obviously, the sum total of all those tasks add value to the whole project, but we don't want to be spending an enormous amount of time, and we don't want to be introducing errors into the system by having to do all this by hand. And then once we have our asset, we have the need to visualize that. So we can create models for visualization, right? So we have the concept of we have an organizational model of all our assets. We can then translate that model into a navigational model. I mean, maybe we want to, not everything needs to be navigated to from an asset perspective, right? Some assets are simply informational things that providing information to a higher level container. And then we can then create multiple application frameworks depending on the real estate that we have. And that's where the variance comes in on an application design perspective. I don't need to be, I need to tell the system, how should I organize this on my tablet? How should I organize this in my control room? My control room's got 3 TVs on the wall and 2 desktops, way more real estate than I have on my tablet. But I want to be able to pick up that tablet and go out to the field and take the same information with me without having to rebuild it, reorganize it, redraw it, do all these things. And this is going to basically say, suck up all the content that I have to show and put it in an organizational model for visualization. In traditional SCADA, we would build screens and then we would put data on the screens and we would navigate to show what screen. Here, let's just build the framework of our visualization, focus on an asset, and the asset tells all the things it wants to show us, whether that's overview screens or whether that's detailed faceplates or data coming from other sources of information. We can have this model adapt to whatever we want. And we do in AVEVA, we do that from our system platforms integrated development environment. And it gives us the ability to define all these things that make up the components of our asset model. And so bringing all that data into the asset model, we can bring in sources of information that come from outside of SCADA, right? We can bring in drawings, we can bring in engineering information, we can bring in stuff from business level systems, we can bring in laboratory information, we can bring stuff coming from other parts of the organization, maintenance information, and put that all into an asset model that defines a more holistic asset, right? Other than just what's the motor speed doing, right? And then be able to visualize that anywhere we want so that we don't have to rebuild everything when we go from a browser to a smartphone to a tablet to a workstation to a control room. So again, assets, basically you navigate to an asset here and then the asset will tell you, oh, all the things I want to see. I've got context information from production. I've got trending information from process visualization. I've got alarming hierarchies and roll-ups that show me where my alarm focus should be. And part of the asset is that it's going to define all how we want to historize information. So we're going to be able to historize stuff from the asset, and we can define how we want to save it, how we want to store it. And then the historian is able to convert that into true information. So we have all these types of retrieval techniques that we can apply on it. We can do interpolation of data. We can do averages, minimums, maximums, integrals, slopes, standard deviations, make predictive retrievals to predict how values are going to perform in the future. Analyze every tag, right? You basically, you can do tags that are stateful, right? Booleans, integers that may be fault codes or things like that, where it's not a contiguous value. Strings like product definitions or work orders or other machine states or other things that can be stored as strings. And we want to know time and state at that point. We want to have minimums, maximums, averages, totals, percent time in those states. So we get instant Pareto analysis of a state analysis, right? And we can actually convert an analog to a state at will just by giving the analog a limit. And now it becomes a state. Is it above the limit or below the limit? How long was it above? How long was it below? How long with the average time up, the average time below, percent time above, percent time below? And also analog uh, time contiguous tags, such as that are also integers, but the integers now have a time contiguous nature to them other than a stateful integer. They can be floats, doubles, times. And we can know the first, last, minimum, maximum, and the time they occurred at. We have an average, standard deviation, integral, value count, percent good. Nothing needs to be configured for this to happen. You just simply put your data into the historian and it will analyze it based on all these metrics. And we can also time slice these metrics. Instead of knowing start time, end time for these things, we can say, hey, give me this stuff when the product code was X or the operator through was Y, or, and be able to do that. You can time slice on any string, boolean, and integer to be able to organize your data in a much more intelligent fashion. Security is also a very important part of our SCADA design, right? And we want the system to be secured at rest and secured in motion. But we have some various things. We can limit what people can do in development and activities. We also limit how they behave in operational characteristics. But this is all done by putting assets into groups and then saying, and then assigning roles to people that can do things within the groups. So can you acknowledge alarms on that group of assets? Can you shelve alarms? Can you modify alarms? Can you adjust configure attributes or operate attributes or tune attributes? Can you actually verify rights that are being asked to do? And you need to secure your system, okay? So systems need to be secured, and the only way to do this today with any degree of practicality is to use certificates. You must encrypt all the data between nodes. You must use certificates to do that. You must prevent anything talking to your SCADA system that doesn't have the proper certificate. Now, that requires management, and certificates are tough to manage. One thing certificates do is they all expire. So at AVEVA, we created a service to do that. We have a thing called a system management service. It automatically secures everything with certificates and automatically manages all those certificates for us, so that when those certificates expire, they're automatically refreshed. In fact, they're refreshed way before they're going to expire. So the system is always prepared so that your certificates are never going to go out of date. And everything gets secured. All communication servers, your operator workstations, if you're using your InTouch stuff, historians, app servers, clouds, batch, MES, work tests, your Pi server, OMI, web servers. Everything gets encrypted and secured with certificates. So you have a great deal of confidence, and nothing's impenetrable, but you have a much greater confidence level of how your system is being protected, right? And then within the SCADA application, you can't forget this part of security. And a lot of security discussions stop at the boundary of the SCADA application. I think that's where they need to start. You need to have understanding of of how is your system going to enforce commands. Is it going to do it based on a graphic, or is it going to do it based on the endpoint destination of the command? It should be endpoint destination. You need to be able to centrally manage this. So we have one place to design it, one place to change it, and it needs to be enforced if in a completely distributed fashion, if that's what you have. Just because you're isolated out at a pump station doesn't mean your security shouldn't work. And everything should be recorded, right? Part of the deal is all user actions are recorded. Every login attempt, every failures, every write attempts to attributes or the equivalent of tags, all these things should be recorded with a write once immutable logging mechanism that's 21 CFR Part 11 compliant. And you need to be able to differentiate things. Not everything has the same security model, right? We have configure requirements. So configure is a security model that says, hey, these things are all related to each other, like the tuning constants, scaling constants of a scaling algorithm. That's maybe 6 or 7 parameters. They're all related. You don't want to change one without changing them all. And you won't want the one to be interpreted until they all have been changed. So operate and tune are just runtimes. View only, maybe you have parameters that you only adjust with scripting and no user interface can change them. Secured write is a validation that the user who is logged in is the one actually making the change. They have to re-authenticate themselves. Nothing to configure on the UI for that. You just put that on the attribute and say you're a secured write, and it'll demand authentication. And verified writes will demand not just two human factor authentication, not multi-factor authentication, but two human factor authentication. We also, multi-factor is easily done also, but sometimes, this is why we put 2 launch keys in a ballistic missile submarine, right? No one's penetrating the submarine. No one's making anything, but we want 2 people to agree to launch those missiles, as morbid as that may sound, right? And you want to do multi-factor authentication, right? The problem is that most SCADA systems are not exposed to the cloud, and they shouldn't be. And so you have multiple intrusion protection devices or firewalls must be crossed. And opening a hole through all your intrusion protection devices is completely unacceptable. You got to have a way of weaving through your intrusion protection in a safe and secure manner so that you can eventually get to a cloud-based authentication to do your MFA authentication. But you don't want something on the OT network that's running your control system in your SCADA to be able to just randomly go to the cloud and do anything they want. You want this to be all regulated and controlled, encrypted, secured in motion, secured at rest, and denying access to any and all endpoints except for those that support your MFA process. And we have a thing called DMZ Secure Link that provides that. It's AVEVA automatically whitelists it from their cloud services, and everything's encrypted, everything's secured. Gives you that ability to enable an MFA authentication when access to the SCADA network does not exist. Alarms need to be managed. We need to be able to configure how they're shelled, historized, adorned, right? How they're logged, how they look, right? When SCADA systems came out, we used to have priorities, and priorities were like 999 levels of priorities. And I always wondered what's the difference between 999 and 998. Really, as you look at high performance SCADA design practices today, we really only want maybe 5 categories: critical, high, medium, low, and then uncategorized. Within those categories, you can use, priority can now be relegated to an alarm subclassification, like this is an electrical alarm that's critical, or this is a process alarm that's critical, or this is a batch alarm that's critical, using priorities for that. But don't, you get too many priorities, just confuses everybody. And, choosing which alarms get adorners, choosing which alarms, so this is on your process displays, little halos be written around the process display elements when things go critical, high, medium, low, when they're unacknowledged, acknowledged, when they return to normal. And this gives us the ability to manage this stuff globally. So you don't have to do this on every graphic. You don't have to do this on every screen that gets built. You just do this in one place, And if you want to change it, you change it one place and one time, and it instantly takes effect throughout all your visualization workstations, web pages, browsers, everything. We want to be able to architect and deploy independent of application design. So in the past, we built big monolithic SCADA containers, right? Which everything was on a single operating system. And yeah, while we could put a lot of stuff in there, it was still limited to the capacity of its host capability. And if we had to ever expand or move to another location, we had to duplicate all that function on something else. And then everything was within the host, all sort of device communications, everything that was there. We ended up having to communicate and design a lot of knowing which host had which data and all sorts of other things. So with system platform and AVEVA, we've moved to a service-oriented architecture where everything now is a collection of services. And the application no longer runs on a single operating system. It runs on a network of operating systems. And the capacity of the application is limited to the combined capability of the network. So if I need more horsepower, I add more horsepower to the network, but my application doesn't change because of that. My deployment model changes, but not my application. And services do all the functions that SCADA had, all the device communications, all the alarm management, historization, storage, retrieval services, visualization, whether that's desktop visualization or thin client via remote desktops, web-based visualization into phones and tablets. It handles all the security, handles all the scripting, so that I now have this array of services. And if I need more of any one thing, I can just duplicate that specific service. I don't have to reduplicate everything that's involved. Right? And so now I'm capable of expanding from a single node to hundreds of nodes, right? It can be centralized, it can be distributed. And the point is I can now put my operations where my assets are located. I don't have to rely on networking comms to enable communication with something. I can make sure that the data is collected, the commands are being able to done. In the case of disconnection of network loss, I can autonomously operate that facility or that station or that remote site from the remote site. I'm not dependent on anything central to make this happen. We can have one system span multiple distributed sites with remote operations, and we can even take multiple galaxies and combine them into a quote unquote universe to give you visualization across multiple plants, multiple plant sites, looking at things from maybe you have a corporate center of excellence that you want to maintain and be able to have process experts that are knowledgeable beyond the knowledge at the plant. And so you can put them all and have one central universal application that can look and operate these things as if they were there. It's the same graphic, same security, same actions, same everything is there as if you were running at the local workstation. And you get full stack redundancy. So, we can talk to we have redundant communications to the devices with redundant paths. We have the automation. SCADA application is fully redundant. Historians are partnered in the fact that their redundancy of a historian must be active-active. You can't have a passive historian and then have it flip over. It's got to have all the data because when you go to the other historian, you want the full historical record. So historians are active-active. Clients are about duplication of clients, and two clients can simply do the same thing. That's the redundancy in clients. But redundancy should take care of lots of aspects. It shouldn't just be data. Redundancy should be alarms. So if I move over from one server to the next, my alarm state is still preserved, but the condition of the alarm, who acknowledged it, when it happened, everything is the same as if it was on the original thing. All operator events are preserved from site to site. And more importantly, redundancy should ensure that the application configuration is consistent. I shouldn't have to node a copy a configuration to a node that was down when I made changes to the configuration last week to its partner node. It should automatically do it for me. And even if that involves software installation, if I installed and added some component to my system and deployed that out to a node, and its partner uh, system was offline for some reason. When that thing comes back online, the node that I is primary should install all the missing software on the standby node and remove any software that is no longer necessary on that standby node. Redundancy should work through application maintenance. It should handle upgrades of the OS. It should handle upgrades of the application. There's never a time when I should have to shut the system down to apply changes. As we move into more cyber critical environments, changes are a mandatory requirement that we have to manage. We can no longer be saying, oh, I'm just going to leave it running at this version that's 10 years old. There's laws and regulations that are coming down that are going to prevent us from being able to do that. Our system must be able to be kept up to date and must be able to operate across upgrades and patches and whatever is required to keep it cyber secure. So part of this whole thing is that there's a great amount of variability in talking to things. You know, we can design the data model of a variable frequency drive, but we may have 4 different vendors of them. We may have the data model of a power meter, but I have different power meters. I may have different PLCs. I have a vast different array of components. And while I can standardize the data model, the connectivity model becomes very, very specific. And in the past, this was kind of a brute force mechanism. We would create individual tags, define an IO point, and we'd go into a spreadsheet and we'd do a lot of work in the spreadsheet and we do things. The problem is that all these, or we'd browse to an IO server or OPC-UA server, an MQTT server, and we'd pick some tags. The problem is these are all error-prone activities. We need to move to an elegant method. An elegant method means that we can define an asset, we can define the attributes that that asset has, and this may all be generated from AI. But then we can build connectivity rules for inputs and outputs, right? And we can add multiple rule sets on the asset and say, hey, this asset's going to use rule set to talk to a Schneider PLC. It's going to use a rule set to talk to an Allen Bradley PLC. We don't want to have to rebuild this thing every time we have a new device come in. And we can, again, AI is great for this. We can leverage AI to design and build these things, but we still don't want to have hundreds of templates that do the same thing, asset templates. We want to have one asset template. This is a VFD, and then it can morph and change its shape as needed based on the type of VFD that we're talking to. We don't want to see things differently either. Operators don't want to have to look at 6 different screens and different ways of visualizing stuff. I think I duplicated this line. Yes, I did. So as we move into the final thing, we want to be able to apply intelligence to check out and testing, right? 100% testing is a failed process, right? It just simply has a human factor error rate, and we generate what we call random versus non-random errors. Random errors are when one asset fails, they all fail. This can be statistically tested for, very high rate of detection, right? Non-random errors occur when I have a one-off occurrence. It becomes very difficult to find. I browse to the wrong tag and now go find it in the 100,000 tags that I have, right? Model design and build practices generate random errors. And then let's get back to the original thing of we have to bid projects and we have to come up with a way of doing this. And so in the past, we would have to understand the design of the SCADA system before we would build it. How many tags, all these metrics, screens, workstations, all these things. We have no idea what any of this stuff is when we're in the bid process of a project. We don't know how big it's going to be. We don't know all the ways we're going to do things. We can estimate it, yes, but the estimates are poor at best. And so within AVEVA, we come up with a way of doing this without having to have to know this in advance, right? We call it operations control. There's a starter version, a site version, a base version, and basically gives you unlimited everything. The starter just gives you a traditional architecture of a primary and backup servers with primary and backup historians, and it's a fixed architecture. The site version gives you unlimited architectures, unlimited everything on a site. Site's a very nebulous term, but it's just basically a site. Doesn't mean it's one physical location, it's one physical site. And it's a user-based expansion, right? So we no longer are counting software pieces, no longer counting how many historians you have, no longer counting how many SCADA servers you have, comm drivers, whatever. So how many people do you have? And you know that because you have a payroll, right? You know what the personnel is. Site goes up to 99 people. Base goes from to an unlimited number of people, but also adds in unlimited sites. So you can have as many things. And this is all fungible and changeable at will with the concept of flex. So you can start at one thing and say, oh, I didn't do that right. Let's go to the other one. But you don't have to rebuy anything. You just swap the thing over and start using a different model. And so you have, starter is your classical system, right? With uh, SCADA A, SCADA B, so to speak, and two redundant or partnered historians, web servers, thin client servers, device communications, and a bunch of clients. Site becomes a more flexible thing where I can remote operations out to remote sites and be able to distribute my application as needed. So my things are next to my assets where they're located and be able to have a much more flexible architecture. And then base basically says I can bring in as many plants, as many sites, as many things as I need. Just worry about how many people I have. So nothing is locked in on purchase, no tags to estimate, historize anything and everything, no need to compromise. Before, it's like, oh, I don't know if I want to historize that. It's going to burn a tag. I only have so many tags. Forget that. You have as many tags as you want. We don't care. Use as much as you want. Put all the clients where you need them, run them on desktops, run them on portable devices, run them on browsers. Do whatever you need to do to make the application successful. Don't architect your application to your licensing. License things should be independent of application demands of architecture. SCADA servers where appropriate, remote or central. And now you get true unlimited scalability, right? There is no limit because you can add in as many resources as you need. And it gives you full stack redundancy, continuous operations through upgrades, patches, and occasional failure. But the administration of your system is has far more greater cases of downtime. All right. If you need to get in contact with me, there's my contact information. I can Mike.Brost on LinkedIn, Mike.Brost at AVEVA.com, and any questions.
Okay, well, thank you, Mike. I do have a couple questions. Audience, if you want to submit questions, please feel free to do so. I will start with, why would it be better to have a distributed system versus a large centralized one?
That's a great question there. Is that, you know, when assets are distributed, I want the functions that talk to them and gather their data and gather their information to be located where the asset is. That way, if for any reason I lose, the most volatile part of this is I'm going to lose communication to the place where the asset is located. But I don't want to lose data where the asset is located, and I don't want to lose any information that the asset has. And furthermore, I may want to be able to operate the asset. I may have a requirement, hop in a truck, drive out to the site, and be able to access that asset directly. I want that to be able to be done in the context of that asset being a part of a larger central system. So I want the functions that need to operate that asset to be located where the asset lives, and full redundancy out there, everything involved. Yeah.
So one final question before I put up my final little slides here. Why isn't implementing an air gap the best security policy?
Well, air gaps basically are a network isolation to the OT network. The problem with an air gap is it's a false sense of security in that it does nothing to protect the application itself. It does nothing to protect the software that intrudes beneath the air gap, right? And while they provide some level of intrusion protection, the greatest threat to our SCADA system comes from within. How is it going to protect from one of your operators whose kids got picked up on the way to school and now he's threatened with some kind of horrible physical violence that he's going to then say, okay, what do you want me to do? right? You have to be able to protect the system from all the threats, not just the external intrusion or malware coming in from the outside. It can come in from the inside too. Stuxnet was a great example of that, right? You have to be able to protect it from yourself. And the only way to do that is with certificates internally.
I lied. There is another question. How much autonomous operations are possible in case of communication loss? What design guidelines to be followed?
Right. So with the service-oriented architecture, all the functionality of SCADA is located remotely. Everything, all history, all alarming, all command control, data collection, store forwarding, everything can be located locally. If need be, you could even put a historian there. So you have full time series history remotely. So the point behind what we're trying to show here is I really don't know how much of that I need until I start building the system. So if I have to build that 2 years ahead of time into a budget, I don't know what I need. So don't architect to licensing, make your licensing give you completely flexible architectures.
So I think that's a great place to end. I do have a couple more slides as we bring it home here. On behalf of CSIA, I would like to thank our speaker, Mike, for this informative discussion. And of course, thank you for attending. Be sure to bookmark the CSIA events calendar so you don't miss any upcoming events. And that's a wrap. Once again, thanks for joining us and have a great day.